Good morning. We are ready to move on into chapter 33. We're going to be looking at lenses. We took a look at chapter 32. 32 had, we learned about reflection, refraction, and then the chapter introduced mirrors. Well, we're going to find out that lenses, the property of lenses, are closely related to the property of mirrors. And in fact, many of the same equations that we used for mirrors when we go through and derive these equations, turns out we can use the same equations for both, which is pretty handy. So on the one hand, if chapter 32 made a lot of sense and you did really well there and you understand all those formulas, that's great. You got a real head start onto chapter 33. If you didn't understand mirrors, this is your chance to understand mirrors also. So by learning the lenses and seeing how things work with lenses, the mirrors, I think, are going to make more sense. In fact, I kind of fall into that second category. When I look at the mirror equations, it's kind of confusing because the light's bouncing off the mirror and it's crossing through the same region of space. Lenses are great, and lenses are great because the light passes through. So it's very clear with a lens, when we look at these problems, if I have a lens of some sort, the light is going to go through one direction and it's going to come out the other side. So when we're analyzing what the light's doing here and analyzing the light here, they're cleanly separated into two distinct regions. So anyway, that's I think of that as a plus. All right, so here's a list of some of the topics here. I'm not going to spend a lot of time here. We're going to be looking at lenses, combinations of lenses, cameras, and we'll also be looking at how the human eye works, or how eyes work in nature. We're going to be looking at some magnifiers, what they're calling magnifier glasses here. And then kind of towards the end of the chapter, we'll look at some basic equations. We're not going into a lot of detail, but basic equations for telescopes, compound microscopes, and then talk about some of the limitations. So it's good to know right from the start, right from the get-go here, that a lot of the formulas that we derive, they're tweaked just a little. There's some approximations that we've used in many of these equations. I almost want to say most of these equations, but that's fine. So we're going to use the formulas that we've derived. We do have to pay attention to some of the limitations that they have. And so this last section is talking about, lenses and mirrors aren't perfect. They're not forming perfect images. And what are some of the issues that we have with lenses? All right, we're going to start off by looking at what are called thin lenses. A thin lens means that the front surface and the back surface are close enough to each other that when we go through and look at how the light is refracting at the front surface and refracting at the back surface, in our derivations, what we can do is consider the two surfaces to be essentially at the same location. So we can carry out one refraction at the front, carry out one refraction calculation at the back, and then we can derive formulas from there. Now, I also want to say this. The book goes through and does some nice derivations of these formulas, and I think they're great. We're not going to concern ourselves as much with deriving the formulas as understanding how to use them. So this is certainly one of those chapters. Now, again, going back and looking at those, looking at the derivations is a really good exercise to go through, but it's not the priority that we're looking at. So as far as lenses, I don't know if you've paid close attention. Maybe you're like me and you've worn corrective lenses for a good portion of your life, either for distance or for reading or whatever. Turns out that these thin lenses can be broken down into what are called converging lenses and diverging lenses. And what converging lenses do is, strangely enough, they converge the light. So light coming into a converging lens gets refracted, front and back surfaces, and the overall effect from those refractions is to bring the light together more than it was when it went into the lens. We'll see some diagrams for that. So for the converging lenses, what we find is if we have what's considered a double convex lens, something that bulges both at the front and the back, when we go through and look at refraction formulas for that, we're going to find that that definitely brings the light together. So that's going to be bringing the light together. Here's one where one surface is convex and the other surface is just flat. And then there's also one here where one surface is convex and the other one's concave. Now, what these three lenses have in common, and what makes them all converging lenses, it turns out, is that if you have the curvature on the front such that the middle part of the lens is thicker than the edges, it's going to be converging. It's going to have properties of overall convergence. Now, kind of an opposite type of lens here. These are referred to as diverging lenses. And diverging lenses, you know, if light comes in towards a diverging lens, when it passes through, it's now spreading out. So more than what it was when it entered the lens. And so we're going to be using these words converging and diverging a lot. We actually used them in the last chapter, or I did. I think it's important to get that converging, diverging classification in place right away. Here what we find is if we have a double concave, a lens with surfaces that kind of bend inwards, when we run the refraction formulas on that, what we find out is this thing is going to be diverging. It's going to be a diverging lens. This one also is diverging, as is this last one. So for the diverging lenses, it turns out that we can check and see, is it thinner in the middle or thicker in the middle? If it's thinner in the middle, it's going to be a diverging lens. Now, if you're like me, and as a kid, I wore glasses I was nearsighted, so in order to bring distant objects into focus, I had corrective lenses. And it turns out that to correct that, we use diverging lenses. Now, if by chance a good portion of the population wears these type of lenses, if you take those glasses off and take a look at their curvature, what you find is they don't make them like this. They don't make them so that they are concave on both sides, or even one side alone. What they tend to do is put a concave surface and then a convex surface on the other side. And again, since the concave surface is more sharply curved than this surface, that's what gives it the overall diverging effect. And so that's the way most corrective lenses. So later in life, a lot of people end up wearing corrective lenses for reading glasses, right? You see these at all the stores. And for reading glasses, we use converging lenses. Converging lenses, the kind of the low prescription ones, look like this. So they tend to be these, the corrective lenses that we use for the most part. If they're really strong reading glasses, you may see some that look like these other shapes. Anyway, that's kind of the shape of what these lenses look like. All right, let's get down to diverging and converging, right? So bottom line is this. If I have a converging lens, like the one that I've got drawn right here, that converging lens, here is some light coming in parallel. So we use that as a reference. That's an easy way to check and see if it's converging or diverging. Let's send some light in that's parallel. Now, parallel light we think of as coming off an object that's very, very far away. So, maybe this is sunlight coming in and going through this lens. Well, if I've got a lens and I'm facing up towards the sun, letting the sunlight go through it, that's a good approximation that light is really, really far away. Or it can just be an object that's, 10 meters away or something, and we can treat that as if the light coming in is almost parallel. So here's the light coming in parallel, and here is somebody carrying out the refraction calculations of the two surfaces. And what we're finding with this lens is that as light passes through different parts of the lens, the different paths come together at a point, or near a point. This is one of those somewhat approximations. So the light comes together and focuses at kind of one sharp point. We call that the focal point. And we call this the focal length of the lens. Now we've already seen this definition with mirrors, so it's just kind of a repeat of what we saw in chapter 32. So they're introducing this idea also of ray tracing. And so what we can do is say, hey, if I've got a lens that has a certain focal point to it, if I draw a series of parallel lines of light going in towards the lens, each one of those paths individually is going to cross through the focal point on the other side. Same thing we saw with mirrors. But again, lenses are my preferred object to work with, easier to think about, because with lenses, everything is passing through the lens. And so the light's showing up over here on the other side. All right, and in part B, what they're showing is this. If we have parallel light coming in from this direction, goes through the focal point. If we have parallel light where all the paths are coming in at some angle, it still ends up landing on the focal, it ends up coming together on the focal plane, but not on the axis of the lens itself. All right, there's an example of our converging lens. Now here's a diverging lens. So diverging lenses, let's do the very same thing. Let's start with a bunch of light. Light's all coming in, parallel, 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 parallel. It hits the lens. Now with the diverging lens, what's going to happen is those paths are going to be spread out. So the light coming out off the lens, out through the lens, is now spreading out, whereas the light coming in was parallel. But it turns out, again, we can define a focal length and a focal point. It turns out that for thin lenses, to a very good approximation, these paths that are coming out of this diverging lens, if we get out a ruler and we trace those back, that they appear to be coming from one particular point. So the light on this side is diverging away from that focal point. If the light coming in is parallel, the light on the other side will diverge from the focal point. And this is, we're going to call this the focal length. Same thing that we did for converging and diverging mirrors. All right, here is a formula. If we go through all those derivations, and again, you can check with the textbook and go through the derivations and the diagrams there. What we come up with is a formula that looks just like the formula we had for mirrors. It says 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And it works. Okay, so now with lenses, we also introduce this idea of the power of a lens. How much power does a lens have? This is not the power from Physics 4a. This is not some number of watts for this lens. What this is lens power, and the power is defined as 1 over the focal length. Now that kind of makes sense because when you think in terms of corrective lenses, for example, a stronger and stronger prescription actually is more and more diopters of power. So a stronger and stronger prescription lens actually has a shorter and shorter focal length. So we kind of flip that over, we use the inverse, and we measure that lens power in units that are called diopters. Diopters are officially inverse meters. So if you look at that formula, we've got units of distance, meters, meters, meters. Power then would have inverse meters, and that's kind of a funny thing to unit to work from. So we just, we call these diopters. All right, so here's a set of rules for ray tracing. We saw this with mirrors. That's what they're saying here. We've got rays or paths that are coming in parallel. We've got ones that are going through the focal points, and we've got one through the center of the lens. Let's see how those work. So, aha, here we go. This is looking like chapter 32, only better. Here is that axis, that central axis that we talked about. Here is the focal point. Now, with lenses, one of the interesting things with lenses is you can flip them around, right? You can take a lens and you can just flip it around and look through them, and they have the same focal length. Kind of amazing. So there's a refraction effect at one surface and one at the other surface, and it turns out it doesn't matter which order those refractions take place. So we can flip our lens around and it will have the same focal length, and so what we can do is designate two separate focal points. Now they call this F prime. I mean, more typically we just see this as F and F. There's two focal points. There's a focal length on either side of these lenses. Now, as far as doing the ray tracing, so for the ray tracing, let's start out with a parallel line. So here's a parallel line coming in, and then it changes direction. It refracts at those two surfaces. And on the other side, something coming in parallel on the other side, on the image side, is going to go through the focal point. So there we go. Now, the object they have here, they've got this arrow. So here is the point, the tip of the object is the particular location that we're following paths of light from. So that first path, parallel and then through the focal point, path number 2 that they've used here is through the other focal point. So we're going to always have two focal points, and that means that we can always draw a path for each one of those focal points. Each one of those focal points will give us a path in our diagram. That's always going to be the case. So, so we've got that second path. Now, when we see where those two paths cross each other, that's going to tell us where the image is located. So we really only need two paths in order to determine where the image is going to be located. Now, just to check, I always think it's good to draw that third path in. And this is often the path I start with rather than waiting till path number 3. And that's to take a path right through the center of the lens. So I can take a path through the center of the lens, and since if I'm going right through the center, these lenses are thin, that says that the front and the back surface of the lens are essentially parallel planes, and whatever refraction we have at the first is undone by the refraction at the back. And so the overall effect is for that path to sail straight through. All right. Now, yeah, they're saying all that stuff here. Now, a couple of other things we want to keep in mind here. This is a real object. The object is really here. And the way I can tell from the diagram it's really there is because I drew it. And it's got these 3 paths of light spreading away. So if I have a real object, it's going to be located on the upstream side of the mirror, of the lens, sorry. And I'm going to have paths of light, 1, 2, 3 in this case, moving away from the object towards the lens. I think of that as the object light, or the light associated with the object. So those 3 paths kind of describe where the object is located, right? Now on the other side of the lens, there's the image light. Those 3 paths are associated with the image. And they converge at this particular location. And what that tells us is we'll have an image plane at that location. Okay. So, and now they've got these eyes. I think we saw the same thing in chapter 32. I think they're confusing. I've been removing them from most of the diagrams here because, well, I wrote some stuff in here. The human near point, the point at which we can focus, is considered, in normal vision, is considered to be about 25 centimeters away. So unless my eye is 25 centimeters away from that image, I can't focus on it. Okay, so it's just kind of a blur. And often in these diagrams, they have these eyes right up against where the image is located, and you're not going to be able to focus on that image. Anyway, so it's a real object to a real image, and that's kind of the easiest setup we can have is if the object and the image are both real. Now, what we're finding out here, same thing with mirrors, is if we do go from real object to real image, the images, there's going to be an inversion that takes place. So the image will be inverted relative to the object's orientation. Okay, so that's a good starting diagram to work from for practice. Because the diagrams get harder. You know, this is kind of the easiest diagram. Again, if thinking, well, I have to look at it to have this image here, we don't need somebody to look at it in our diagram. So I'm not going to worry about that. Or I'm going to actually try to think of that not even being there. All right. What would happen if, this is an interesting question they ask, example 33.1, what would happen if we half block a lens? What if you cover up half of a lens? What's going to happen? What happens to the image if we cover, for example, the top half? And I think to see that, let's go back and look at this. This is a good example. So let's say we have an object, we have a lens, and we've got an image. We have some kind of a screen set up, and the image is showing on our screen. What would happen now if we covered up the top half? What would happen to the image? Would we only see the bottom half? Would we see the top half? What would happen? And from these diagrams, what we can see is, well, how many different paths did light take to get from object to image point? And it turns out that light passed through every part of the lens. So there are many paths that the light takes in getting from object to image. So if I block half of those paths, if I cover up half of the top half of the lens, I'll still see the entire image. Every part of the image, there will still be paths going through the lower part of the lens that take us from object to where the image is located. It just won't be as bright. So by blocking half of the lens, the entire image will still be there, only half as bright. Same thing with the lower half. If I block out the lower half of the lens, I'm going to see an image that is only half as bright. Okay. All right. So human near point 25 centimeters. Okay. Everything seems good. All right. And that was our question. Ooh, okay, so we've graduated. We've moved on from converging lenses to diverging lenses. Let's see if we can still find those three paths. Now, path number one that we talked about was we picked a point at the tip of the object as our reference, or as the point we're going to start from. And then we followed one line in parallel. Now, remember, this is a diverging lens, so instead of light bending towards the focal point on this side, it's going to bend away from the axis, and it's going to bend away an amount that lines it up with the focal point back over on the other side. Okay, so, and that's worth staring at for a while. Okay, path number one, oh yeah, it's a diverging lens, I get it. We're going to be using this focal point here rather than this one. Now that was for path number one. Remember, there's a second path that uses the other focal point. Now this at first might seem a little confusing. You go, well, I've used this focal point for path one. How do I use this focal point on the other side? And what we did for the converging lens was we took a path headed towards the focal point, but not this focal point this time. This time, path number two is going to be headed towards this focal point. But what happens along the way is it runs into a lens. And when it runs through the lens, that lens is going to create a diverging effect. Think about this. I had a path of light that was coming together, something that was kind of converging, and then when it reached the lens, it bent away from its convergence. Well, that's diverging, right? So something that diverges relative to the path that entered the lens. finally, we can take that third path. Well, even with these two paths, let's see, I guess we better line a few things up here. So what's complicated this diagram is, in addition to the solid lines showing where the light is going, I've got to have these dashed lines. These dashed lines are going to be oriented with different paths, and I'm going to use those along with my ruler and my straight edge when I'm drawing these, because you guys want to draw these, get some practice drawing them. The midterms will typically ask you not just to do calculations, but also to draw some of these diagrams for these lenses and mirrors. Now what this is telling me is that these two paths, path number 1, which corresponds to this dashed path right here, and then path number 2, which corresponds to this path. So again, let's go back and talk a little bit about object light and image light. Object light consists of these three paths, 1, 2, and 3. Now notice these three paths easily traveled through the air and all reach the lens. Now what's happening on the other side is we have what's happened to those three paths is now they're diverging relative to what the path was on the other side. So these three now are more spread out, and this is our image light. And so to see the effects, we actually have to trace back paths 1 and 2. Paths 1 and 2 of the image light have to be extended backwards to find out where the image is located. Okay. So again, what we've done is we've done two paths. We know where the image is, or as long as we haven't made any mistakes. In order to confirm or get a little more confidence, we can try a third path. So here's a third path right here. Here's a third path going through the center of the lens, and if we've done everything correct in path 1 and 2 and found out where the image is located, path 3 will follow right along with that image location. So path 3 will line up with that. Okay, so we've got the three paths, the three image paths, 1, 2, and 3. And if I follow those back, all three of those image paths line up with that point. Okay, and so that's telling us that's where the image is. Now notice what's happening here is I had a real object. This is not a real image anymore. The light doesn't really come from that point. We have to use these dashed lines to work backwards and find out where it's coming from. But the light isn't truly coming from that point, or it's not reaching that point. So this is a virtual image. It's not real, it's virtual. Now for this setup, for the real image and the virtual, or the real object and the virtual image, there's no inversion. So we managed to avoid the inversion for this. Okay? All right, a couple of good examples to work from. Okay, so the thin lens equation is very similar, it's identical, to the mirror equation. 1 over f equals 1 over do plus 1 over di. Here is kind of a standard diagram of where the dos and the dis and the focal lengths are on the diagram. So we've started with a lens. Now, it's common to draw the lenses so that they bulge a little bit if they're converging, or they're double concave if they're diverging, and that's fine. You don't have to do that, and in fact your drawings will, well, the correct way to do the drawing is to just consider the plane right at the center of where that lens is located. Okay, so it's really just that plane that we want to consider. So everything's measured relative to that. So if I think in terms of that plane, measure back to where the object is, that's my object distance. If I think of that plane, measure it back to where the image is, that's my image distance. And then the focal lengths we've used the focal lengths to draw in two focal points that we can work from. Okay, and again on this diagram I've actually labeled it and said that these paths represent the object light, these paths represent the image light. Now the formulas are the same, but remember with the mirrors and now with lenses, the focal lengths, the object distances, the image distance, they can all be positive or negative. So they can all be positive or negative. And so let's take a look at that and see how the signs work. They work the same way they did with mirrors. The focal lengths, if a focal length is positive, that indicates a converging lens, or vice versa. If it's a converging lens, it's going to have a positive focal length. If it's a diverging lens, it's going to have a negative focal length. Now with the object and image, ooh, that's supposed to say DO and DI. With DO and DI, a positive value indicates it's real, or if it's real, then we're going to write it down as a positive number. Virtual is designated with negative numbers. So watch the signs. Again, same as with mirrors. When we're working with lenses, one of the best ways to keep track of what's going on is to do both a diagram and the calculations. Do both. And then double check and see if your diagram and your calculations are telling you the same thing. They should be consistent with each other. This is just a list. I'm not going to... I guess we got to go back and do one more. Let's see. I didn't include that in the table. The HO here and the HIs are going to have opposite signs. They can't both be positive. They can't both be negative. One's got to be positive. One's got to be negative. And probably it's more common we say the object is, the HO is positive, and then put the negative signs on the images that show up from that. So not just the DOs and the DIs, but the HOs and the HIs also are going to have signs associated with them. Okay, and that's what all of that writing is saying, so I'm not going to worry about it. Here's the magnification formulas. Now this is what's called lateral magnification. So going back to our diagram here, lateral magnification is comparing how far in the sideways or lateral direction, how large is the image compared with how large is the object. And so how much does it extend from that central axis. So it's a sideways measurement that we're thinking in terms of lateral magnification. And the formulas that we have for this, obvious enough I hope, is that HI divided by HO tells us how much magnification we have. All right. Now it turns out because of some similar triangles going on here. Let's go back. Notice that I have a right triangle here, and I have a right triangle here, and that these two angles match. So I've got similar right triangles. That says I can use ratios on all the sides. So what that says is HI is to HO as DI is to DO. So the ratio of the heights is going to match the ratios of the distances. Okay, that's easy enough. Now the thing though we have to keep track of here is, but what about the signs? Because in this case, HI is negative, but the DOs and the DIs and the HOs, everything else is positive. Well, to correct for that, or to correctly represent that, in the formula, we can get the magnification from HI over HO, or we can get it from DI over DO. We got to put a minus sign in. So it's another minus sign you have to keep track of. And if you're good with keeping track of minus signs, you're set. That's a very good sign. If you lose track of minus signs, you're not as set. Okay, anyway, that's the formula for lateral magnification. And then the plus or minus sign on the power is going to match whatever the focal length is. So that power formula is going to work the same way. Okay, so this slide is pretty much just saying what we just talked about. That draw ray diagrams, and then use some math and solve the formulas. Make sure you're following the sign convention, and then make sure that your calculations match your ray diagram. All right, here's an example. Example 33.2, and what this is saying is here is an image formed by a converging lens. It's really kind of similar to those other converging lenses we were looking at, except the new thing here is that the DO is really large. The DO here, 100 centimeters, compared with the focal length, it says here that the focal length is only 50 millimeters, or 5 centimeters. So the focal length on this lens is 5 centimeters, but hey, we place the object 100 centimeters away. That's like 20 focal lengths from where the lens is located. Now they've drawn a nice diagram. They've drawn a nice ray diagram. These can be tricky, right? If you've got one of these diagrams where the object is way out here a long ways, that's going to make a difference in getting your ruler out for a straight edge and drawing everything very carefully. But let's see how this thing works. I'm already a little nervous about this, the images that they've drawn here. But let's go ahead and see. So let's see. This leaf is right side up. This leaf is inverted. That's kind of what we've seen. They've got lines 1 and 3. Remember I said 3 is my favorite line, or maybe the easiest one to draw. 3 just goes right through the center. So they didn't even bother with line 2. They just went right through the center, and then they used path number 1 coming in parallel and used the converging properties. So here it is. Here is my calculation of all this stuff going on. So oh, it is. It's a camera. Okay, I missed that part. Sorry about that. This is a camera. So what's happening is the light is coming through the camera lens, and it's a single converging lens, surprisingly enough. So it's a single converging lens going on here. The DO is 100 centimeters. They told us the image size is 7.6 centimeters. Okay, so that's the size of the object, and then the focal length is 5 centimeters. Now I think we introduced these diagrams back in chapter 32, but let's just remind ourselves how these work. You're not required to use these, but I sure think they're handy. If we take the formula, this one right here, if we take this formula, 1 over F equals 1 over DO plus 1 over DI, and we plot that with DI as a function of DO, it looks like this. It looks like hyperbola. The 1 over F is a constant because F is a given value. And then varying the DO means how close am I going to move the object from the lens. So I can actually show image distances as a function of object distances. Now for this, what we find is that we get hyperbolas. So here are a couple of hyperbolas here. And the hyperbolas are at, they're not lined up relative to the origin, they're lined up relative to these asymptotes. The asymptotes are at DO equals F and DI equals F. And those are all the possible combinations of DI and DO that we can get with this lens. So let's plug some stuff in and see what's happening. Now, this is the formula we're going to work from. We know what DO is. We know what F is. We can plug those numbers in. 1 over 5 centimeters minus 1 over 100 centimeters. Those are both positive numbers. And then the DI worked out to be 5.26 centimeters. So that's where I am predicting the image is going to be located. Now that's 5.26 centimeters. That's not very far past the focal point. If we go back and take a look at this diagram, and it seems to match. I mean, we did the diagram right, and the diagram came out so that the image was just a little bit beyond the focal point. That certainly looks like our diagram that we drew. So that's where the image is going to be located, and it's going to be a real image. That's a positive number. And the magnification here is given by minus DO, or DI over DO. So that's going to be minus 5.26 over 10 centimeters, over 100 centimeters, sorry. And that gives us a magnification of minus, there's my minus sign, 0.0526. And I just, just inverted that number to see what it turned out to be. Turns out that the magnification is minus 1/19. So that's telling us that the image is 1/19 the size of the object. And it has to do with this ratio right here where the DO was like 20 times the focal length and the image distance turned out to be one less than 2019, 1/19 in terms of size. All right, now on this diagram that, that we said maybe you want to start using these and get some practice, or maybe you decide they're just extra baggage, we don't need them. On this diagram, what this is telling us is as the DO gets larger and larger, as DOs get really, really large, the image distance is going to get, the image location is going to get placed closer and closer to where the image location is going to be closer and closer to where the focal point is. And that's what we're seeing with this setup. And so it's a real object going to a real image, and the solution is right here. It's in the real quadrant up in that corner. Okay, let me go back and take one more look at that, because here's my concern. I don't know how you guys feel about this, but what they just told us is that, see the size of the object over here? Let's take a look at the size of the image. That object is supposed to be 19 times bigger than the image. What do you think? And I don't think they got it scaled right. I don't know how that happened. Oh, maybe, you know what? I don't think this is 5 centimeters. I don't think that's 1/20th of that distance. So it's not a good, ray diagram. It's not good ray tracing. But again, as I mentioned before, when you get these objects that are way out there, it's hard to keep everything accurate with the ray diagrams. Okay, so they tripped up a bit there. All right, here's another example. Here is the an object close to a converging lens. So here is the converging lens. And remember, all the examples that we've looked at so far, the objects were over here, outside the focal point. Well, this is asking, or showing, what's going to happen if we bring an object really close to a lens, close to a converging lens, and let's go back to our diagram here, our functional diagram. If we bring that close to, if we start bringing the object in closer and closer, what's going to happen is we're going to get an image that's pushed farther and farther away from the lens. See how DI is getting bigger? And then it's the asymptote. And you guys know from your math classes, functions like this hyperbola, things just radically change when you cross that asymptote. Now, physically, where that asymptote is located is that asymptote's right at the focal point. So going back to the diagram here, by taking the object, which has always been outside the focal point up until now, and moving it inside, we go from, the object is still real, but instead of having a real image, we're going to have a virtual image. Let's see how that works. That's what that math graph was showing us. So let's try doing paths 1, 2, and 3 here. It's a little trickier. So let's start with this. Start with path 1. Path 1 is parallel, it comes out, it's a converging lens. So I'm going to bend the path of the light. I'm going to reposition it so that it passes through the focal point. Okay, so that was easy enough to draw. Now, the problem here is, well, I've used up that focal point. How do I use the one on this side? So the light's going to be heading in this direction away from the object. What we do is we orient the light coming away from the object as if it's coming away from the focal point. Now the light didn't really come from the focal point, so it's going to be a dashed line that we have there. So I'm going to have this dashed line, and it's going to travel up here to this lens, and then since it's coming from the focal point, as if it's coming from the focal point, it's going to come out parallel. So you can see in this example, the light coming into that converging lens is spreading out so rapidly, the object is so close to the lens, even though it's a converging lens, it's not going to be converging enough to bring the light back together. So we're used to thinking, hey, light comes into a converging lens, the converging lens brings it back together. What this lens does is it takes light that was really spreading out, paths 1, 2, and 3 here, with 3 going through the center, was spreading out a lot. The light spread on the other side isn't spreading out as much, but it's still spreading out. So it is a converging lens. It did bring the light together somewhat, but it was not able to create a real image. So we're going to be left with a virtual image, and if we trace these lines back, path 1, 2, and 3, so here is the trace back for path number 2, and here is the trace back for path number 3. I think those are the easier ones. And those cross each other here. So it says that the image light, which I've labeled here, and object light, the image light is spreading out, and it's spreading out in a fashion where these 3 paths look as if they're coming from that point. Okay. And we've traced all 3 of these lines back, so again, it's a good one to practice with. Good diagram here for these examples. Okay, and then here are the numbers. I guess we could, this actually, that's probably a good place to stop. Oh, let's go ahead and just wrap this one up. We'll probably take a look at this example when we're starting out when we come back from break and come back for the second part of class today. So I'm just putting numbers in here, and these were all on that page before. So they're telling us that we have an object distance of 10, a focal length of 15, and that's it. That's all we need. They're not giving us object heights. So we'll start with that. So here it is. Focal length is plus 15. It's converging. Object distance is plus 10. It's a real object. And then 1 over di is equal to 1 over f minus 1 over do. I plug the numbers into here. I'm getting a di that is negative 30. So remember that number. I'm getting a magnification also that is plus 3. So I'm getting something that's bigger, and it's quite a ways on the virtual side of the lens. Let's go back and look at that. because that's what we're supposed to be doing, right? Checking to make sure that we're making the right predictions here. So the object itself was here. That's 10 centimeters. And then this is 15. This is 30. Seems right. And then the image is going to be 3 times as big as the object. The image also is going to be virtual. All right. And I crossed the eye out on this one. I crossed this eye out. You might actually be able to view this. Let's see. In order for the person to be able to focus on that image is going to need to be 25 centimeters away. And it is, right? So this is 25 centimeters here. So maybe the eye can stay in this time. So this would be someone holding up a lens, not right against their eye, but rather holding it out at some distance and then placing an object behind it and looking through it to see the image. Okay. And then the last item we can take a look at here is, this is the diagram that goes along with that right here. And so what's happening is we're not doing this real image, real object stuff. We're down on this other part of the function. We're down on this part of the function that corresponds to an object that's closer to the lens than its focal length. And as a result, we're getting a virtual image. So in this quadrant right here, the DOs will be positive, the DIs will be negative. And it's a DO value of 10, it's a DI value of negative 30. I roughly plotted what point on that hyperbola corresponds to those numbers. Now, if you want to use these diagrams for slope, the slope's also in there. What you can do is take a line from the origin out to the point that represents the DO and the DI values. And take the slope of that line, and that will give you the magnification. So it's DI over DO with a negative sign on it. So the magnification is 3. All right, we'll stop there, take a break, and then we'll come back with more lens stuff.